Hello, welcome everybody. Amazing to have all of you here again. I'm just looking through the chat right now and it's incredible. We have over 1,000 people registered from all over the world. It's really a global audience. Amazing to have you all back here with us again. And we're looking forward to another amazing evening with an update from Jason. Ruben's going to give you a little bit of an idea of what's going to be happening over the next couple hours, and then we're going to pass it over to Jason. So go ahead, Ruben.
Absolutely. Super exciting to be with all again. Literally, as you said, Mischa, from all over the world. I can see Johannesburg and Isle of Man and Los Angeles, all over. Thank you for being with us today. And a couple of things just to give you a little bit of a program and agenda. So first, as usual, Jason is going to present the update of the build of our aircraft. That's going to go for about 35, 40 minutes. And then we're going to have all that Q&A. And it's always lovely to see questions from all over the world. This time we have outgrown the Zoom capacity. That's why I have a platform now. It's going to be like this every single month. And we're going to have the chat for that. So you can have and put your questions there. Mischa and I are going to pick up the questions, one each of us. And then we're going to ask Jason to answer those. So welcome again. And most importantly, Jason, welcome to this live update of January 2022. The floor is yours.
Thank you very much, Ruben. Thanks, Mischa, and welcome everybody to Hill Helicopters from around the world. So we've got an action-packed presentation for you this evening. We're going to focus on 4 primary areas. I'm going to give you a broad sweeping update of the progress the company's making. We're going to talk quite a lot tonight about the GT50 turbine engine because that's a major focus of activities here at the company at the moment. Talk a little bit about the work that we're doing on the drivetrain for the aircraft, the gearboxes and some of the clever work that's going on there. And then we'll finish up talking about the composite airframe and how we're beginning now to move from third scale all the way up to the full-scale production fuselage. So lots of exciting stuff to talk about, and we'll get into that straight away. So if we start with an overview of the company and the progress that we've been making here, for those of you that are joining us for the first time on a Q&A, as a company, our vision is very clear. We believe that the helicopter can be much more than it is today. Something that's more capable, more attainable, more desirable, more connected and more owner-centric than ever before. And when you deliver a product like HX50, HC50 and the whole ecosystem for how we want these aircraft to be operated out in the world, it's not surprising then that the market resonates with you. So in terms of our performance out there in the world, we're now up to 432 aircraft across 40 countries. That's 373 HX50s and 59 HC50s. So we're absolutely delighted with the support that we've been given from around the world, and that really is a big motivating factor for everybody here in the team in the UK and our other staff around the world. So thank you very much for the support. We're absolutely delighted that the products are going down so well. Of course, with a big order book and the need to deliver this aircraft, the team is also growing. I think I mentioned in some of the customer updates over the last couple of weeks since Christmas that we're currently advertising for a further 8 technical posts, and there's some more to come. We've been promoting some of our key people internally as well. So Martin Watson has now taken on the role of lead airframe systems engineer. We're going to talk more about the work that he's doing later. And Stuart Marshall has picked up the role of lead GT50 engineer. So he's looking after a lot of the value engineering, the production engineering, and pushing that GT50 into a manufacturable artifact that we can get on the bench and test. So very, very pleased with the performance of these guys and the team in general. It's all going really very well. So that's all great. In addition to that, you'll be aware from the materials that we've pumped out on the various platforms that our vertical integration agenda is crucial to the way that we deliver this aircraft to the price point and in the timescales that we're indicating. And as such, as we continue to move towards the prototype build, the DC facilities are growing and expanding to meet those requirements. So the major things that are going on in the DC at the moment in terms of building the capability, building the business to build the aircraft, is we've now procured a very, very advanced coordinate measuring machine and a metrology suite. So this is a temperature controlled environment that's going to be fitted just over there that allows us to measure to extremely tight tolerances and extremely high degrees of precision and accuracy the precision components that we make. So the compressor, the bearings, the gears, and a lot of the internal components for the engine and some of the flight critical components. So that's a very key capability that we've taken our time to get the right kit there, because there's a lot of options out there. So I'll talk a little bit more about that later. You can actually see the LETS machine that we've purchased in the top right hand corner of that slide. In addition to that, we'll talk a little bit later about our annular combustor, but in addition to switching over to the annular combustor, we're actually having to also develop all of the manufacturing processes to be able to deliver the sheet metal work in these complex, high-grade, nickel-based super alloys to be able to form those parts, weld those parts, fabricate those parts. And so there's a lot of work going on at the moment with a number of experts, both in the company and outside the company, to bring that capability in-house. And as I think, again, I've mentioned on one of the customer updates, although these materials are very advanced, and although the combustion system that we're using now is really state-of-the-art, the equipment that you need to press and swage and form and weld these materials really isn't that sophisticated. So it's relatively inexpensive equipment that we're procuring there. Another big area, of course, is the casting capability. We've had all of the proposals back now from our suppliers for the shelling facilities, the wax facilities, the air cast and inert environment casting equipment, and we're in the final stages now of getting that signed off and into the DC so that we can actually cast the key cast components in-house. And again, we're not held to conventionally understood industrial prices for these sort of things. We've brought it right back to what it really costs to make these parts. So very pleased to see that developing nicely. Bit of work left to do on it, but that'll be here very soon also. And then of course the big news from the last monthly update was the successful completion of the third scale fuselage, this single piece composite fuselage that is critical to delivering our aerodynamic performance, our crashworthiness, and the sort of ride quality and the dynamic response of the aircraft. And the very next stage for that, of course, is to get that process in-house so that we can do all of the full-scale work right here at the DC for building the test articles and then also the flying prototypes. So you've been introduced to the infusion pump, which is the heart of all of that, but all of the peripheral equipment now is also on order and will be arriving over the coming weeks. So pleased to see how the general development of the facilities is coming along and keeping pace with the broader development program of the aircraft. So let's go into the technical stuff. Let's start by talking about GT50. As I mentioned, GT50 is now very much the focus of our attention because we need to get that built, we need to get the processes finalized, and we need to get that on a test bench well ahead of when we want to produce the ground running aircraft. So the first thing I'm going to just introduce to you now is where we are across the engine, and then we'll talk about some of the key details. So the engine in the new configuration, so this is the much more compact much more compact vane diffuser, the annular combustor, and the new 9+9 bladed compressor. That is almost at the point where we can freeze the design from a mechanical and an operational perspective. And that then allows us to move into a final pass through stress and lifing, and then we are literally ready to start building all of the components across that engine. There are some of the service routings that need to be optimized. There's an opportunity to take a fairly significant amount of weight out of the engine by optimizing the gas generator bearing housing and also the power turbine bearing housing. And so that's the last area that we're likely to be freezing the design for before it goes through stress and goes onto the bench. And that really gives us an opportunity to have a final push for weight before we put it through stress and lifing. So very pleased with where we are on the engine. I'm very pleased with the engine design, full stop. It's very elegant, very simple. We've managed to avoid building complexity into the engine as we've gone through development, which is often the case. And all of the systems, the turbo machinery, the bearings, the spring bars, everything's looking really good on that front. So pleased with the development of it, very keen now to get it through stress analysis once more and start building these components. So to that end, we demonstrated during the live event just before Christmas that we developed the ability to produce compressors in-house. Now the compressor that we produced was a 10-bladed unit that was derived from an original 12-bladed design that had been passed off aerodynamically. With sort of working with both the production engineers and the aerodynamicists, it became clear that the optimal solution was going to be around 9 blades with 9 splitter blades. It's a little bit more challenging aerodynamically because you've got less guiding for the flow. It's more difficult to get the work that you need to into the airstream. But with a fair amount of CFD optimization and a lot of experience from our compressor team, we've now managed to get the performance in terms of the overall efficiency of the impeller and also the stability of the impeller, its surge margin, to a point where we're almost like for like with the 12-bladed design. But of course, this affords us significant advantages from a manufacturing point of view. We can get much bigger tooling into the cavities, we can machine the impeller much faster. And the other advantage, of course, is that because we're using bigger tools, bigger ball noses, it means that we have bigger root fillet radiuses at the roots of the blades that you can see on that impeller, and that improves the structural strength. It reduces the peak stresses in the compressor, so improves both our fatigue life and also our burst margin on the impeller. The other thing that's been developed over the course of the last month is the drive couplings and the self-centering couplings on the shaft. We have to impart nearly 1,500 horsepower into this impeller at its maximum operating speed. So we need to be able to drive that, and we also need to be able to start it from the starter generator. So what you can see on the slide there is we've added the sort of sawtooth couplings at the front and the rear of the shaft, which are known as Curvix couplings, and they provide the drive mechanism. They also provide the self-centering features that you need to make sure that the shaft can remain aligned, balanced, and properly centered in its bearings. So the details for that have all now been finalized, and the production guys are busy now developing the cutting techniques for all of that. The other thing that I may have pointed out to some of you that were here with us last month is when you take the compressors, the other thing that we have to do with these things is pressurize the back face of the compressor within the engine. So we create this labyrinth seal around the back face so that essentially we can pressurize the outer diameter and bleed off the pressure on the inner diameter to manage the axial forces that this compressor generates by virtue of the pressures it generates along the shaft of the engine, and so manage the life and durability of the bearings. So those sealing features have all now been optimized, and they're built into the machining operation and the compressor itself. So really pleased with where we stand on the compressors. The titanium from which we'll actually produce the test article is on its way to us now, and we'll shortly be producing 6 actual test specimens of the impeller to the design that you can see there on the screen. So pleased with how that's moving. There's a little bit of development work to go back and do on the compressor test rig now to allow us to test it, but that'll be also underway shortly. So in terms of how we actually manufacture these components, one of the real benefits of our vertical integration strategy is the fact that all of the stuff that you generally need to do after you've built and developed your prototype and you're trying to upscale to production, we're doing right now. So what I'm showing you on the screen here is our second generation approach to how we produce these impellers. So the picture you can see in the top corner is the CAD model of the lathe that sat right behind me over there, and it's a new form of work holding that allows us to cut the blanks from a plain bar, both front and back, in a single operation. So by holding the compressor stock in a more intelligent way, we can machine everything that we need before we plop the machine on the 3-axis for the Curvix and then the 5-axis for the blade cutting. And that dramatically simplifies the number of operations that we need to produce the impeller and the speed with which we can produce the impeller. So what you can see there is that unit that's now developed to sit on the lathe can also fixture on the 3-axis machine to put the Curvix in, the 5-axis machine to then go and cut the blades and all the other details. So the whole production process for the impeller has been dramatically improved over the course of the last month, as well as the design and the mechanical detail of the compressor. So that's all coming together very nicely. The other thing, of course, once you've got the process down to a point where it's stable, we then need to make sure that we're making what we think we're making. So one of the other areas that we've been developing over the course of the last month is the capability to measure these complex blade shapes to ensure that the blade geometry is what the design intended it to be, and that the process for cutting, stress relieving, finishing the cuts, and everything else that we need to do to the impeller to cut away all that excess material is doing exactly what it's supposed to. So the coordinate measuring machine allows us to essentially automatically plot and measure the entire surface of these compressors, and this is not only a development process that we use, but it'll also be a quality control process that we use as part of the production process for these parts. So when the thing comes off the machine, not only do we know we've got a quality part, but we also know it does exactly what the design intended it to. So this is critical not only for the aerodynamic performance of the impeller, it's also imperative for the balance of the impeller. But as I think I've mentioned to you before, that a very significant amount of both the efficiency of the impeller and also the surge margin derives from the tip clearances between these blades and the casing that the compressor sits in. And if any of these components are not manufactured to drawing, then you lose all of those tolerances, and so you lose a lot of your performance and stability in the compressor. So this is the process that we use to control all of that. The program by which this will be executed has been developed by our CMM partners, and all of this kit will be coming in-house shortly. So very pleased with the whole compressor program. It's exactly where it needs to be at the moment. So in addition to the compressor, you're aware that we've moved to the annular diffuser, which you can see there in the green. Both the aerodynamic design of that and the structural and mechanical design of that is now stable. There's a few minor areas where we're likely to refine that over the coming weeks before we finally freeze it, but essentially we've got a very, very simple arrangement now that has the minimum number of parts while still giving us the structural stiffness, the isolation of the pressure and thermal loads, and the integrity at the seals that we need to be able to hold the tolerances around the compressor that we need. So pleased with the way that's coming on. In addition to the diffuser, what you can see on screen there is the compressor, the diffuser, and also the annular combustor. Now, the annular combustor is a fabrication made out of nickel-based superalloy sheet material. So the design of that has now essentially been frozen from a performance point of view. The pressure drop, for the most part, for I think almost every area of the design envelope is below what we've included in the performance calculation, so we should get better performance out of it than we've been predicting. The cooling, the way these devices work is we bleed cool compressor delivery air over the surface inside and out of the combustor to maintain the metal temperatures well below the flame temperature of the combustion system. That's how you get the life, that's how you get the integrity of the combustor. And so the optimization of the whole distribution, the cooling patterns has now has got to a point where we can't learn much else short of just building and testing the thing. So a lot of the focus over the last couple of weeks has been about design for manufacture, designing the tooling, breaking out the parts that are going to be pressed or the parts that are going to be rolled, looking at how we can assemble the thing, because it's quite a quirky shape to actually make, looking at the jigs and rigs and the fixturing we need to do all of this, looking at the welding process. There's a couple of material choices that we are still up in the air at the moment that we need to essentially choose whether we use an expensive material without a protective coating or a less expensive material with a protective coating. And there's some trade-off studies going on there to make sure that we get to the life both cyclically and in terms of hours that this unit's designed to. So pleased with how all that's going on. The background video that you can see there is the first test specimens of materials that we've had in. They've subsequently gone out for weld trials. So we're tuning the welding process that we're going to use to be able to assemble the subsequent parts within the combustor to deliver that complex shape that you can see there. The other thing that's been going on as well is, as you can see, the whole annular combustor works on using a very large number of precision holes. So there's about 2,100 holes in the annular combustor casing. All of those are very tightly toleranced. They're very sensitive to their position, their roundness, their shape, and their surface quality within the bore of the hole. And so we're looking at a range of processes to maximise the value engineering that we can do to actually produce this part in a cost-effective way. The raw materials are not that expensive, so it's all won and lost on how you actually fabricate it and how quickly you can put these things together. So that's been a particularly successful piece of work that's been ongoing. We've drawn a couple of specialists out of retirement to support with the actual metal forming, guys that have worked on these combustors for a number of other engine manufacturers over the years, and their kind of knowledge and insight when you're picking up these sorts of things is absolutely invaluable. So we've got a very straightforward way to produce these things. We're just about to start actually designing the press tools and the rollers we'll use to actually form the parts, and then we'll be producing one of these in the coming weeks. So pleased with the process on the annular combustor also. The other big area, and it's been the last of the turbo machinery elements to be formalised, is our turbine nozzle for the first stage of the gas generator turbine. So this is the hottest part of the engine that sees the worst thermal cycles, that sees the highest thermal stresses, and needs the most care to ensure that we don't end up with an inadequate cyclic life or premature failures when we put it on test. Originally, we'd hoped to do this as a solid ring, but the more we've looked at it and the more we've optimized it to hit the levels of performance that we want across the wide range of operating conditions that we need, we've ended up opting for a cooled nozzle. So what that essentially drives you to do is, rather than making it as a ring, you end up making it as a series of segments that have to be hooked into place in a retaining plate in the engine. And these rings themselves have holes in the top of the platform and the bottom of the platform, and they bleed cooling air through the center of the hollow aerofoils and out through the trailing edge of the blade. And this allows us to run the engine hotter than it would otherwise have been possible to do, which of course improves your fuel efficiency and your power density, but it also means that we can control the metal temperatures in these parts somewhat better and ensure that we hit the cyclic life that we need to hit the performance that we've declared as part of the GT50 specs. So another area that is almost, very nearly complete now is the mechanical design of the power turbine. So GT50 has a rear power takeoff. So the drive shaft that actually turns your main rotor comes out the back of the engine and then mates with the speed reduction gearbox that we'll show you the casing of shortly. Now, all of these shafts within the engine essentially have to have a suspension system like your car does. So they're mounted in what are known as spring bars. So the grey component that you can see on the slide there is designed to be a lot more flexible than the engine casing itself, and to isolate the modes of vibration of the shaft, the rotor dynamic modes, from the casing stiffness. And that allows us to essentially maintain the shaft stably in high speed rotation while the engine's operating, in this case, at 36,000 RPM. So what you can see on this slide here is we've essentially designed a very intricate spherical coupling that sits within a spline shaft that drives into the main rotor gearbox, and that essentially allows that power turbine to bob around cantilevered in the spring bar damper and maintain nice stable operation with the degrees of freedom it needs to isolate it from the external sources of vibration. So that design is also complete. We had been doing some work on trying to use a Curvix coupling to see if we could simplify the manufacturing process. That's the coupling you can see between the drive shaft and the red blisk itself, but it looks very much like that's not going to be the optimal way of doing it. So we'll probably end up returning to a friction bonded means of attaching the stub shaft to the back of the blisk. But essentially, the new blisk is aerodynamically designed. It's now structurally designed. The drivetrain's all looking good. We've managed to design the coupling into the speed reduction gearbox and get that to a point where we're satisfied it won't fret and it'll be reliable, and that's all looking very good and is very, very close now to being frozen. The only thing, as I say, that we're pending now is just hopefully being able to shorten that shaft a little bit as we deal with the secondary air systems. Okay, a big area that we've been working on quite quietly in the background is our in-house casting capability. So a little while before Christmas, we carried out some casting trials where we melted down some super alloy and cast a nominal ingot using an inert environment casting process rather than a vacuum casting process. And the idea of this is if we can make that work, then it allows us to use essentially machinery that's drawn from the jewelry industry rather than the conventional hugely expensive vacuum investment casting furnaces. And so those trials were carried out by our casting specialist, and what we found is that essentially the process does work. So what we've subsequently done is we've taken the specimen that we cast and we've put that under a scanning electron microscope to have a look at the microstructure and the crystal structure of the cast components that we produced. And if you look at the two pictures that you can see on screen, the one on the left-hand side of the screen is the raw material, the superalloy going into the induction furnace. And then on the left, if you look very carefully at that picture, what you'll see is the pattern that you can see under the microscope is comprised of what we call cubic precipitate crystal structures, which is precisely what you need to be able to get the high temperature performance out of these materials that it's critical for the performance of the blisks under high temperatures. So we've proven that process. Moving on from that, we've also now secured all of, as I said earlier, all of the casting equipment that we need to be able to carry out this work. And so we're now in a position to essentially bring the casting process completely in-house and have complete control over what would have traditionally been the most expensive parts of a gas turbine engine. So we're very, very pleased with the process that we've made on there. That's great news. So casting looks good. If we now talk a little bit about the drivetrain for the aircraft, there's been a vast amount of detail work going on this. So the drivetrain itself has been fairly stable for over 6 months now, and we're very much down in the weeds now dealing with all of the intricate details that you need to make these things reliable and manufacturable and to have the long life that all of these components need. So one of the areas that our sort of drivetrain, powertrain lead engineer has been focusing on is the lubrication system for all of the gearboxes. So what you're looking at here is the drivetrain that's strapped to the engine. So you can see the speed reduction gearbox at the back of the engine. I'm going to take you over to the bench in a second and show you the housing for that we've just been machining. We just finished the machining off of that this month. And then you can see the drive shaft that essentially goes forward into the bevel box and then up to the main rotor gearbox. Now, what we've done now is we've essentially completed the scheme design for all of the lubrication system for this. So the engine and the engine drivetrain share a lubrication system, and it's a forced lubrication system to make sure that we've got the right quantity of oil delivered at the right places, particularly in the critical areas of the gearbox up at the very, very high speed end of the gearbox. So we've now got a stable lubrication system, and essentially the next step for this is essentially build it and test it. So when we come to look at the tail rotor gearbox in a second, I'll talk about how we test the lubrication system and how we validate all of that. In addition to the gearboxes themselves, all of the helicopter pilots in the audience will be well aware that one of the critical areas of the drivetrain for a helicopter is the long, flexible tail rotor drive shaft. Because typically these drive shafts, if they're not correctly designed or not correctly maintained, will suffer whirl instabilities and can tear themselves to pieces. Now, in order to keep the weight sensible, we can't run this below its first natural frequency. You have to run these shafts supercritical. So one of the things that we've been tuning over the course of the last month is the rotordynamic modes of vibration of the drive shaft and optimizing the way we do the damping, the way we do the couplings, and to try and pull as much weight out of the shaft itself as we possibly can. So what you can see on screen there is the first 3 modes of vibration. So these are the shapes, the rotating shapes that the shaft will want to take up at speeds that are important to us. And what we're able to demonstrate, we're not quite there yet, but we'll be able to comfortably keep the 60 to 140% running range clear of any resonances. So that's well outside of the rotor RPM range that you would ever see in normal operation or under the most extreme emergency conditions. So the tail rotor drive shaft looks in good shape at the moment. And our favoured approach for this, like with lots of areas in the aircraft, is going to be a carbon fibre drive shaft, because it gives us improved stiffness, improved rotor dynamics, improved damping, and of course it's something that's nice and easy for us to manufacture in-house with our composites capability. So the whole drivetrain system now is very mature, and we're just really waiting on some test articles to come off the equipment and to get some of these things out to test so that we can validate that the thing does what we think it does. So at the last update, we showed you the first stages in manufacturing the main rotor mast, and we've now completed that. When we had the live event last month, we hadn't yet received the live tooling that's required to cut the splines, which are the tooth features that are on the top and bottom of the rotor mast. Now you need those teeth to be able to drive the rotor at the bottom and then drive the rotor head at the top. And all of those things have now been completed. So if we just quickly have a wander over to the bench at the back, I'll show you the rotor shaft as it's come off the machine, and we can also show you the speed reduction gearbox casing, which has also now been completed. So at the previous live event that we did, we were able to demonstrate the cutting of this external profile of the main rotor shaft live on the machine, and subsequently we've been back and added the teeth at the top and bottom. So just so you understand, this is the bottom. It's this face here that carries the entire weight of the helicopter. And then you've got various other sealing faces and assembly features along the shaft. The only thing that's not complete in this at the moment is we're waiting for a boring bar so we can go in and remove the excess material from the outside, and then that essentially is the vast majority of the mast manufacturing processes completed. All we need to do then is switch over to titanium to produce the flight components. One thing I will point out on here is in this first attempt we've had at producing these spline features, you'll notice that one side of the teeth has a nice high quality surface finish, but there's a bit of pickup on the other side of the teeth. Now you couldn't live with that. We can't leave that in there. That's got to be improved, because that would be a devastating source of fatigue problems for us. So things like that have to get ironed out at this stage before it goes anywhere near a test rig on the ground or otherwise. So that's the rotor mast. That's shaping up very nicely. The other thing that you will have seen last month is we'd machined the outside of the speed reduction gearbox. So this is the actual speed reduction gearbox that sits on the back of the GT50 engine. So your power turbine sits here. That 36,000 RPM drive shaft drives into the top, and then within there we've got all of these locating features to pick up on the bearings and the other gears to be able to do the speed reduction, to then export 6,004 RPM, I think we are, are at the moment, at the bottom, and then out to the rotor gearbox. And again, this is really the first one that we've taken off the machine. There's a lot of tidying up left to do on the inside of there. There's some surface finish issues that need improving. And of course, this is a case that we're going to use purely as a fit and finish demonstrator, a lubrication demonstrator for the first gears that we produce. The actual test articles for the engine will be cast and then finished machined, which is a much more productive way of making these things. It's a much more efficient way, a much more cost-effective way of making these things. But it's good to see that's off. It's good to have these components lying around now. And then just to give you an idea of scale for those of you that have not seen the customer updates, this is, I've taken one segment out that I showed you earlier, but that's the first stage cooled nozzle. So the component I introduced earlier, that gives you a sense of the size of that. And that thing handles between 1,500 to 2,000 horsepower worth of energy in the gas stream. It's got to take that flow, stabilize it, turn it into the right direction so it presents at the face of the first stage turbine blisk in the right angle with the right velocity. So it's a very, very critical part, and it's the one that causes most of the problems in most of the engines that are out there. So it's important to get that developed very tightly before you go anywhere near a test rig. So pleased with how that's coming on. Before we head back over there, I'll just point out these components here. One of the things I'm going to talk about shortly is our in-house bearing manufacturer. So the very first thing that we're going to do is produce some of these bearings and demonstrate that we can produce the same fit, finish, tolerances as some of the other bearings that are already out there. We're going to be starting with the races. Of course, when you do the races, we can then add flanges and details that make assembly easier, that reduce the weight of the arrangement, and then we'll go on and do the more difficult ones that are integrated with our spring bar dampers and the big ones that are in the main rotor gearbox. But all of that we'll talk about shortly. So let's head back over and I'll just talk to you about a few other things. Okay. So one of the other components that we're working on at the moment is the tail rotor gearbox. So we showed you a full assembled tail rotor gearbox previously. It's actually sat on the tail fin over there, fully functional. What we've got to do now is bring the hardware inside that gearbox up to production standard. So these are the gear blanks that we had made, again, just before Christmas, and the production engineering team are now busily taking these blanks and designing all of the work holding, not just for these gears, but for all of the gears within the aircraft, so that they can hop from one machine to another behind me and have the teeth cut in them, get the heat treatment, and then be picked up and relocated and clocked into position on the machining centres, ready to have the hard machining done as a final operation. So all of that's coming on very nicely. In addition to that, the lubrication system has now been completed for the tail rotor gearbox also. That will just be a simple splash lubrication gearbox. We've got a little bit of work to do on the chip detector, and we need to increase the size of the sight glass. But other than that, the design of that gearbox, both the drive mechanism, the Thomas couplings, and also the pitch change mechanism is nicely stable. That's very, very close now to well, that in fact is ready for its first stage of testing. So this is the aluminium casting casing that it contains the tail rotor gearbox. It's a spare one that we've got from building the test rig behind me. And one of the things that we do to assess how well the system is being lubricated is we replace the metal component that will actually be on the system with a translucent component, so we can actually physically see what the oil's doing in there. And so we can run the aircraft through all of its orientations, all of its different speeds of operation, and just physically look inside and see what's going on inside. So although we've got all of the different advanced simulation methods at our fingertips, sometimes the old ways are the best, and being able to see what's going on in engineering is always a massive advantage. So the tail rotor gearbox 2 is also in a very good place. So we're now on with the gears, and then we'll be able to get that onto a full system subtest. Okay, The two single biggest priorities for the company at the moment in terms of our mechanical development are the manufacture of the full range of gears that go on the platform. So gears and bearings are the mechanical engineering jewellery that define essentially the quality of the drivetrain of this aircraft. We've introduced to you previously the way that we intend to make our gears to control the cost to the best extent possible for these sorts of volume applications. We've developed the process using industry partners that have worked with us. We've now brought all of that capability in-house. The machines to do all of this work are sat right behind me, and one of the biggest activities we've got going on within the company at the moment is the development of the first set of HX50 and GT50 gears that we can then put on long-term fatigue test. So the very first gears we're producing are the ones to go up to Newcastle to be tested and produce the SN curves that form the basis for qualification for the rest of the system. But while we're doing that, we're also producing all of the main rotor gearbox gears, tail rotor gearbox and engine gears. And so we're developing a unified work holding strategy, a unified tooling strategy, a unified heat treatment strategy, so that we can apply essentially the same process for all of these gears. So that's underway at the moment. It's one of the single most important things that we're doing. Don't expect that to be a 5-minute job. That's a big job. There will be development setbacks along the way, and there's a lot of work to do to get that to just where it needs to be to produce these extremely high quality parts. In a similar vein, the other big area is the development of bearings, as I've just shown you over there. So aerospace bearings are very, very expensive, and there is not really a need for them to be expensive. The quality controls and the surface finishes and the performance of these things, by and large, are no different in a light helicopter that they are in other bits of industrial machinery. And so we've essentially brought the capability to produce bearings in-house. Our Klingenberg K10 internal and external grinding machine is now commissioned and operational, and we're just about to start essentially producing the first hill-made bearings for both the GT50 and the HX50 aircraft. So we'll be starting with the production of the races and all of the metrology that needs to go into that, all of the measurement and the quality control that you need to get those components measured, matched and running to the right tolerances. And then assuming once we've done that, then we move on to the balls and rollers, because at the moment we can still procure those externally cost effectively. So in-house bearings and gears are the primary focus of what these machines are doing behind me at the moment, and that really is the single biggest factor that goes into the cost of the mechanical elements that make up the helicopter drivetrain. So it's a really important part of the development process that's the primary focus of what we're doing right now. The final technical area that I want to just cover briefly this evening is the airframe. So as you will recall, just before Christmas, we showed you that we'd successfully proven our infusion process. So working with composites integration and our specialists and their specialists, we were able to take carbon fibre in its lowest cost format, lay that into a high quality tool, and then infuse that with a high quality resin and deliver aerospace grade, high volume fraction carbon composites in a single piece. So we have this lovely monolithic structure. What we've got to do now is optimize that process. So Tim and Tim are back together, the band's back together. They're down in Saltash at the moment, and they're looking at some of the learnings from the first off that we pulled out of the tool. So they're improving the surface finish, they're improving ways of holding that dry fabric. We're looking at some different fabrics that we can use for that. So we've got the spray tack that we've introduced before, but there's also other processes by which you can apply tack and attach the fabric to the mold. And the guys are working through some of those options at the moment to push all of the complexity and the cost and the variability out of the process to give us true aerospace grade composites ready for when we produce the full-scale unit. The other thing that they're doing, which of course you need to do for a full-scale carbon aircraft, is the lightning strike protection. It's vital in a composite fuselage that you have adequate conductive paths built into the fuselage, so that if you are unfortunate enough to be struck by lightning, it doesn't vaporize the fuselage or cause large-scale structural damage. So we use the standard copper mesh that's embedded within the laminate. But of course, again, with dry fabric, it's much more difficult to place that. So the guys have been developing a very intelligent way of holding that stuff in place within the laminate so that we can produce these components and deliver all of the elements of performance we need from them. Then the two other big areas that the guys are working on are working the process up to full scale, both in terms of the process parameters and also the tooling. And then we need to, of course, bring all of that production capability in-house so that we can control the cost and the scheduling and the quality of these components going forward. So big focus on the Airframe at the moment with the composites team. We've got both a drive on the processing side, and then also I'll just indicate some of the design issues that we're dealing with too at the moment. So Martin is currently leading the airframe systems element. So an airframe isn't just a structure, it does lots of other things as well. So things like how we do the transparencies, the forming, the tooling, the coatings that they need to protect from IR and UV, and also the bonding of the transparencies onto the composite are all detailed elements of the design that have been finalized at the moment. The same with doors, the little things that you don't think about, hinges, locks, seals, trim panels, all of that stuff needs to be nailed down before we can do the final pass through stress engineering. And so all of that's going on right now. I'm going to introduce some interesting things that we're doing shortly on lighting. So there's some really fantastic opportunities in improving the landing light capability and the night flying capability with modern LED lighting, and there's a lot of work going on that at the moment, as well as some awkward issues to do with the forward fuselage packing with the trimmer tank, the flight controls, the undercarriage, and all of those sorts of things. So lots of progress moving in those supporting areas as well. One of the trials that we've been doing this week with one of our suppliers is looking at just how much lighting capacity we can get into the space available for the landing light. Obviously landing off airport in a VFR helicopter really at night really requires great landing lights, and modern LED lighting gives us a great capacity to deliver that. So we're currently developing a trial where we're going to take various lighting modules and try those before we finalise the actual optical design of the landing lights, because we really want to be able to light that whole area like a Christmas tree and make night flying as safe as it can be. So lots of selection work going on with specific lighting modules before we finalise the packaging of that. The other big area in the fuselage that we've been doing recently is the crashworthiness. So we've talked about the way we're delivering the energy absorption within the crashworthy stroking seats previously. We'd looked at a lot of metallic-based systems, and we finally opted for a carbon fibre based crush tube just because of the energy density of the stuff, its ability to absorb energy, and its lightweight. We've successfully completed the static testing of the crush tubes. You can see the tube on a machine there being completely pulverized by the downstroking, which is how you absorb the energy. And we've got dynamic tests booked shortly so that we can look at the strain dependency characteristics of that as well. And then as soon as we've got that, we can finally size those crush tubes and freeze the design of the crash seat as well. So the whole seat can be built and tested at that point as an entity. So really pleased with how that's developing. And of course, in parallel to all of this, we're pushing harder and harder at the moment to finalise the full-scale airframe. So there's an awful lot of structural analysis being going on over the course of the last month using modern finite element methods. So this is looking at optimizing the laminate, optimizing the layup, optimizing the geometry, and getting the most robust, most damage-tolerant structure that we possibly can. And that work is now got to a point where the structure is more than strong enough. It's comfortably within the weight target as it stands at the moment, but we do have opportunity to pull more weight out of the structure, and that's what Tim's focusing on at the moment. But again, we're very close to freezing that concept, and then the only thing that's left to do with the fuselage then is to go and capture the little bits, all of the interfaces to all of the little things like the doors and the controls and the things that you want to attach to the fuselage, so that we can build those features into the final stress model, and then that's ready to be frozen too. And at that point, we can produce the first test article and start pushing and pulling this thing for real. So across the program, we're delighted with progress. The engine, the airframe, and the drivetrain, as well as the other areas I haven't had a chance to talk about tonight, are shaping up very nicely. So at that point, I'm going to stop talking for a while, and I'd like to hand over and give you the opportunity to ask any questions that you might have. Thank you very much, guys.
All right, Jason. All right, Jason. Well, we're not going to give you too long to be able to stop talking, because we have lots of questions for you. Wonderful questions that came in. So we've got a good list of them. And the first one is about the world going electric. And a lot of people talking about electrification of aircrafts. How do you see the future of electrification for Hill helicopters, electric motors being integrated, and things like that?
So electrification offers fantastic opportunities for a conventional helicopter. The idea of being able to independently drive the main rotor and the tail rotor at different speeds, not have them mechanically linked, is fantastic. It gives us some huge opportunities from a performance point of view. It gives us some huge opportunities from a noise point of view, and it dramatically simplifies the drivetrain for a helicopter. So being able to electrically power a helicopter is fantastic, and I can assure you we will be all over it just as soon as it's the right time to do it. The problem that you've got is the energy density of batteries and even hydrogen, if you want to look at that, are just not there yet to make it viable to do it in a helicopter. It would just cost you too much performance. So a better route in the short term would be to take HX50 as it stands at the moment as a conventionally mechanically driven helicopter with a gas turbine that is fundamentally capable of running on sustainable aviation fuels and biofuels. So we can deliver substantial carbon neutrality with the conventional drivetrain that we've got, while we give the engine tech guys enough time to bring the batteries or energy storage methods to the point where it makes sense to have a full battery electric helicopter. Or an intervening step would be to go hybrid. And hybrid again has huge opportunities for a light helicopter. Essentially, just by using something not much bigger than the battery you have to start your engine, meet the certification requirements, you'd be carrying enough energy in that battery, if the battery was designed correctly, to be able to fly for a very significant amount of time in the event of an emergency. So it's quite realistic, just with today's technology, to have a minute, 2 minutes, maybe a little bit longer of flight time in the event of an engine failure with something not much heavier than conventional helicopter batteries for starting the engine. Now, what that does is it means all of the horrible bits of the helicopter operating envelope, when you're close to the ground, going into a confined area, coming out of a confined area, if the engine stopped at that point, it would just turn into another landing. You know, it wouldn't be a difficult spot to get yourself into and out of with a botched auto rotation. And the same with our target market, which is private owner operators, people that don't necessarily fly all that often. To have the peace of mind that in those awkward bits of the flight envelope, if the engine did stop, you'd still have a minute or two, would be a massive advantage. And so again, when the technology is right, when the time is right for that, we will probably go hybrid as a next step and stick with the sustainable aviation fuels as a source of power, right up until battery density means that a battery electric helicopter would be meaningful. But the moment you go electric drive, the moment you get rid of the tail rotor gearbox, the speed reduction gearbox, the bevel box, the main rotor gearbox, you get rid of all of that mechanical drivetrain weight, sticking a little permanent magnet generator on the back of the engine and having a main rotor motor and a tail rotor motor does seem very appealing on all fronts. So we will go that way. It's not the right thing to do right at the moment. It's certainly not the thing to do right out of the blocks, but it will come perhaps in around a 10-year time scale, 5 to 10 year time scale at the absolute earliest. But right now, the best way to make the best possible helicopter for private owners is just do a really good job of a conventional helicopter that can run on biofuel, and that's what we've done.
Okay.
All right. Then Sean Gordon asks, will the HX have an auto hover feature?
If you take the 4-axis autopilot, yes, it will.
Okay. Is that going to be something that's straight out of the box, or is that going to be a future update that comes out?
It should be straight out of the box.
Okay. Great. Next question then is from Noel. New interface is very shiny, and oh, sorry, that's a different one. How are you making out with supply shortages? What's your plan with supply shortages, and how is that going to impact pricing?
It won't impact pricing. The whole beauty of vertical integration is that essentially all we're bringing in through the front door is raw materials at their lowest value point. So we've got the greatest insulation to that than you can possibly have. There's nobody stacked up on top of it. There is some fluctuations in material prices. I think when we originally looked at titanium for the compressor, it was about £1,000 per compressor. It's currently, in prototype volumes, it's currently at about 2,000. But I think that will stabilize by the time we get into production. And even with that kind of inflation on selected parts, it really doesn't hurt us. So there's no danger of the price going up beyond what's stated in any of the purchase agreements. We're solid on that.
Great. That's actually a frequent question that we have, Mischa and I. And now a question about the build school. Tony Berry, in early presentations, the direct involvement of owners in the build cycle was tablet. Is this still the case? And is there a case for involvement in the ownership model for non-flying members who have a greater interest in the life support? I think it's about the build school regarding flying members and non-flying members.
Yeah, so the build school is absolutely a feature of HX50. You can't have a HX50 unless you come to the factory and build it with us, be part of the build school. It's an integral part of what we think it takes to be a safe, independent owner-operator. We need to give you that knowledge to be able to operate your helicopter out there in isolation without the support of a chief pilot watching over you. So that's absolutely part of the business model. And we will probably do something similar, not quite the same, but something similar for HC as an option, and let people that want that knowledge to come and do it as part of the safety course and see some of the part of why we do the build school is because I want people to understand that when you make aircraft, you can only really make them just strong enough. And often people believe that there's big margins where there isn't, and people need to see how we test them, how we develop them, how they go together, what's important. So that's very much in the DNA of the company. So build school is not an option for HX, you have to come.
Okay. Next one is from Fernando. What are the overall flying restrictions from the HX50 versus the HC50?
Essentially, HX50 cannot be used for commercial operations. Now, the definition of commercial varies subtly around the world, but certainly for the simplest way to explain it is you just can't do hire and reward. Most places you can't do flight training, and that's about it. In terms of operational limitations, they're very much based on the basis for initial certification or initial approval. So if you meet the certified code, you get the same privileges as any other aircraft that meets the certified code. So in terms of the aircraft, it's day-night VFR, 5 passengers, and you can use it as any other day and night VFR aircraft.
All right, that's clear. John Aponte asks when are we going to see the HX50 and the look of it with the floats, deploying floats?
It's the very next thing on my list because to finalise the fuselage, we've got to put the pockets in. So it's something that's right on the top of my list at the moment. So expect some schemes for that to be shared over the next month or two.
Okay, thank you. The next one is from John, and he's saying, can you compare the specs of the HX50 to other similar aircrafts like the R66, 505, or the EC120?
Yeah, it's a lot. Not off the top of my head. It's a simple answer.
Tough question.
In terms of most of these aircraft, I think the thing that we've done with HX50 that the others can't do is the whole aircraft has been designed around being able to put a 95 kilo passenger in each seat, 3 hours of fuel on board, and then fly at 140 knots. And there are very few other aircraft, well, there are no aircraft, in fact, that can put that weight of passenger in the seat, put 3 hours of fuel in, and then fly at all, let alone fly at 140 knots. So it is a step beyond what any of the other similar platforms can do. The other big thing, and it's not something we talk about very often, or haven't in recent Q&As, is the CG range for the aircraft. We've got an articulated rotor head and we've got an active fuel management system. So we have a little trimmer tank in the nose of the aircraft that essentially will give you almost carefree CG handling. So we can, with everything from a sort of 70 kilo solo pilot all the way up to 595 kilo guys in every seat. Sorry, that's 70 kilos with some baggage as well. You will always be within CG range. So you haven't got the criticality of CG limiting what you can pick up as you have in some of the other helicopters. So it's a very well-rounded, well thought out platform. And then the other thing is we don't have all of the limitations of the aircraft are lined up properly. So the engine is designed to deliver up to 500 horsepower. The transmission is designed to absorb up to 500 horsepower as part of its stated overhaul life. So you can use all the power that you're entitled to use. So you've got 400 horsepower continuously, 440 horsepower for 5 minutes twice every hour, and 500 horsepower for 30 seconds twice every hour. And you can use that till your heart's content and it will meet overhaul because we've lined everything up to be able to do that. So I think the way I would compare it is we really wanted to deliver a machine that would never run out of power, would get you there faster than anybody else, and would give you carefree loading and handling. And I think that's what we've done.
Great. Jeez, we have so many questions. Okay, the next one. Is it possible to use load cells on the landing gear for accurate weight measurements? This comes from Roy Godkin.
Yeah, this is a lovely question, and this is something I really, really want to do. So, obviously, you've got a gas spring in each of the oleos, and so reading the pressure seems like a really obvious thing to do. The problem is there's quite a lot of friction in the oleos, and so you're limited in how accurately you can measure the weight if you try and do it the nicest way, which is just to read the pressure in the oleos. So we're looking at ways to do this because we want an out of CG or an over gross weight warning to be automatic as part of the digital cockpit experience. We don't want any gotchas. So it is something we're looking at, but the most obvious way that you can think of doing it won't work in practice. It won't be accurate enough. So it'll require some other form of sensing, and we haven't decided what that is yet.
Okay. Question from Darren. Can you give us an approximate timeline of when the engine will be bench tested?
In the summer. So
okay,
yeah, we're building bits right now and getting those to a standard where it's worth testing them. The test rig's got to be brought up to speed with the latest geometry, and then we'll get the compressor on test. Literally as soon as we can cast blisks now, we'll do the burst tests. So that's a very simple test where you put it in a box and spin it until it explodes. And then there's a bunch of other tests that we'll be doing shortly as well. So those will all be ahead of the actual full engine test, but we're aiming to have an engine on test in the summer.
Okay. From Neil Henry, we have any views regarding the recent news of Enstrom filing Chapter 11?
I think it's really sad. I've spent a little bit of time flying a 280FX, and they're really nice, really robust helicopters, so it's a shame. I think nothing is forever, you know, and I think any business that doesn't move with the times will eventually run out of steam. And I think if we've learnt anything from what we're doing is we've got a very clear signal from the market about what expectations are for helicopters in 2022, and any manufacturer needs to move with those times. Otherwise, I think they'll struggle. I don't think we had any impact on Enstrom. I think it was probably COVID that was the final straw, and the lack of private flying, the lack of parts and things like that being required. But I find it very sad. It's a shame to see any company like that go. So I'm sorry for everybody involved.
Absolutely.
Yes, I agree. Yeah. Another question, so a question from Jim. He says he has a Turbo Mecha today that he is using 130 liters per hour. Turbo Mecha says that they will manage in the future and cut consumption by 40%. Why is that the GT50 is consuming about the same amount of fuel?
I don't actually know what they're doing to justify those claims. I don't know whether it's a duty cycle thing or whether it's a hybridization thing. You've got to understand gas turbine technology, the fundamental thermodynamics of gas turbines mean that the only way to get more efficiency out of a gas turbine engine is to run the turbine hotter and to use a higher pressure ratio. The higher pressure ratio is pretty easy, but the turbine hotter is very difficult. I showed you these nozzles and the extent that we've had to go to make these components to stand up to the cycles and to stand up to the ravaging thermal stresses that exist in an engine. And we're using the very best material on planet Earth for this. There is nothing better anywhere. So there isn't any materials to do that any better like this. What we then have to do to run these better is go to even more intricate cooling, have lots of holes in the blades, do film cooling over the blades. We then have to do that on the blisks. So rather than making those single piece blisks, we'd have to have individual blades with fir tree roots and pipe air through those to cool the metal and keep the metal cool enough that it could withstand that environment. So it's a very big, expensive job. And you've got to ask yourself, what value does it add to a private helicopter owner? Because your fuel bill is irrelevant. It's not a major cost. Your depreciation, your maintenance, your insurance will dwarf those costs, the cost of fuel. So the question about fuel consumption is really the environmental one. And our answer to that would be stick with a robust engine and solve the carbon neutrality problem with using sustainable aviation fuels and biofuels. So we've just got a different answer to the same problem that doesn't involve making a fantastically complicated engine that will just drive costs. We're all about being pragmatic. Fuel bills to a private helicopter owner are irrelevant.
All right. Igor asks, would you recommend our helicopter, HX50, the first helicopter for an inexperienced pilot?
Yes, absolutely. My kids will learn to fly in a HX50. So why? I think that it's designed for inexperienced pilots. No other platform, perhaps save Enstrom or perhaps save Gimbal. Most of the helicopters that find themselves as entry-level turbines and other piston helicopters are not really designed for inexperienced pilots. Everything that we've done in configuring HX50 is about making everything as easy as possible. So, I mean, Mischa can probably talk to this question as well as I can, but there are lots of things that you need to do in a helicopter to make it easy to fly. So first of all, power. You know, everything's easy in a helicopter when you've got power. Confined area landings, departures, handling all sorts of ends of the operational envelope. If you've got power, everything's easy. So we've designed the helicopter with a big gross weight so that it'll always be well below its gross weight when you're operating it. And then we've given it a big power to weight ratio. So it's got loads of power compared to other helicopters that you might choose to learn to fly on. On top of that, we've got this lovely, benign, high inertia main rotor system. So when you're learning how to do your power failures in the hover, when you're learning to do your auto rotations, you've got all the time in the world, in relative terms, to react, and then plenty of stored energy at the bottom to drop the thing onto the ground. I also think when you're training for auto rotation that the wheels are a big advantage. They're a big advantage in learning to do rolling takeoffs for minimum power and rolling landings for minimum power operations, and they're a great way to practice auto rotations all the way to the ground, because now we can just do that to a runway and land like the aeroplanes do. So both in terms of the power available and the rotor system, you've got a benign three-bladed rotor system, no mast bumping, much better behavior in gusty winds. I think the only thing I would say to balance that argument is it has got a very big tail. And so the weather vaning effect will be slightly stronger than it would be in other helicopters. So you'll have to learn to cope with that. The other thing, every helicopter comes with a 2-axis autopilot. So just being able to take the workload out of flying, just to be able to keep the thing the right way up when you're overwhelmed. That is a standard feature, and that's not a standard feature on any other helicopter in the market. And again, that's one of the benefits of vertical integration also. The other thing that I would say is, of course, the digital cockpit is designed to be as simple and easy to use as possible. All of the instruments are huge by comparison to what you're used to, and those sort of middle-aged eyes that many of us have got won't struggle with these big, bold, colourful gauges. The panel itself only gives you the information you need. There's no clutter. There's no throwing information at you that you can't process when the workload is high. You can just concentrate on having your eyes outside and fly. The haptic power manager that we've got in the collective means that you can feel how much power you're using and how much power you've got left. So when you're doing those higher workload maneuvers as a novice pilot, like coming into confined areas, you can feel how close you are to your power limits. Your eyes don't need to be inside. So for those reasons, workload reduction, increase of margins, and of course the huge crash worthiness that we get with this composite structure, all round, I don't think anybody can touch HX50 as a platform to learn to fly on. But once you get that license, it's a license to learn, and you've got to go out into the big wide world and build your experience. And you really want a machine that's going to give you the biggest safety margins in all of the areas and all of the ways that you're going to want to operate. And that really is absolutely what HX50 was targeted to do.
Great. I think that's a very clear answer why you want your kids to learn on HX50. That's great. All right. So Mike Stute says Rolls-Royce, previously Lucas Aerospace, has about 1,000 people designing fuel pumps, metering units, FADEC controls. How are you going to manage to certify the fuel system, which as a flight critical component will need to pass high and low temp, shock, vibration, contaminated fuel test, endurance, etc., etc.?
Quite simply, we'll do those tests, and it doesn't take 1,000 people to do those tests. My previous business was running an engineering company that used to go in to these big companies with big teams full of people talking about doing jobs rather than doing jobs, and then go and solve the problems that they couldn't solve. You don't need 1,000 people to do these sorts of things. You need the right people to do these things. And our team is a mixture of young, dynamic engineers coupled with often guys that have been retired for many years. I've got 90-year-olds heading up my combustion. I've got 80-year-olds working in the fabrication of the combustor and stuff like that. We've got lots of people with all of the experience, all of the been there and done it and seen it before knowledge to contribute and deliver the fuel system and all the other systems on the aircraft. We've got people supporting us on all areas to be able to deliver this. So it doesn't require that number of people. That's a fallacy. That's just what happens in big businesses and what happens in defense projects.
Don't need to copy that. So our friend Steve from Canada.
Lost sound. Oh, there you go. We're back.
There you go.
We're back.
Yep. Steve from Canada asked about the GT50. Where do you expect failure from here to flight certification? There's always a fallback. So for each, do you pre-engineer fail-base design changes, or do you address it when you see it? What is the plan for any context impact to the schedule?
Yeah, it's a mixture of the two. So in terms of component matching, we engineer slight variations of key components to match the compressors and the turbines and the nozzles. We've got to tune the mass flow through the engine so that the gas generator runs at the right speed to develop the right mass flow and pressure ratio. And you will always get that wrong. So we engineer from a design point of view to be able to change those things very quickly. And of course, I'm sat right in front of the machines that are going to make these parts. The guys that are going to design these parts are in the office right up there. So when we test it over there, if we have any problems, I've got to walk about 50 meters in that direction to get it changed and then drop it back on the machine. So unlike a traditional structure for producing these things where there's lots of different companies involved, you're never important to any of them, and huge timescales, we can do it all here. And so we So
Carry on.
I've got Siri coming on and off on your laptop. So yeah, essentially, many of the components are designed to so that we can do drop-in replacements on the tests. The other ones allow us to simply engineer replacement parts very quickly with the in-house capability. So that's how we'll handle it.
All right, and Mischa is back. Jim Haydal, have you set a time to when you want to present how the maintenance program will work? POH, when can we expect to get it?
Those sorts of things will be right at the end of the day. We've got to finish developing the thing, get it to the point that it works. We've got some performance pages, some calculated performance pages for the POH ready, but of course those aren't the ones that you'll use. They'll just be survey pages. They were just sanity checks that we'd got the envelope that we wanted. So I'm afraid that will be right at the end of the day.
Mm-hmm.
Okay. If you guys can hear me, that Dave has a question about mono mold airframe. So I think the monocog structure, how difficult would repairs be on that structure?
I think on balance, no more difficult than it would be for a traditional metal structure. So you've got to remember, this is a flight critical structure where it isn't the ultimate load cases that get you. It's that little bit of damage that you do that looks innocuous that becomes a fatigue crack and fails at some unexpected point in the future. So with any aircraft, you have to be very careful about what you repair and what you don't. The beauty of the way that we've done the monolage is most of the things that you actually see on the outside are non-structural panels. So the doors are massive and protect the load-bearing frame. So if you bump it or knock it or it gets some hanger rash, it's simple replaceable components or repairable components that we don't really care about that much. The same with the windows and the transparencies. Large amounts of surface area are replaceable components. The big baggage bay doors on either side, the tail boom's separate, that can be replaced relatively inexpensive. There's a stinger cap on the bottom of the tail fin. I don't know if you can see it behind me over there, but the bottom part of the tail fin beneath the fenestron is a removable part that's crushable, and you can crush that without doing any damage to the main structure. So there's lots of common sense areas like that. It will be possible to repair a composite structure. Again, at the end of the day, a composite structure is just a bunch of fibers in some glue. So as long as you can restore the material to the level it was before, then you can do it. But it's just the moment it departs from what we've done the structural tests on, it becomes very difficult to guarantee that you're going to have the fatigue life that you would want everybody to have. So ultimately, if you do enough damage, you'll have to swap the monolage or the boom or a panel. But you'd have to go a very long way to do that. I think there'd be other bits of damage everywhere else if you'd gone that far.
All right. Jim asks a very practical question. Today I have to wait 3 to 6 months for parts, especially if it's part of an engine, gearbox, or hub. What can I expect from you, Jason?
We will carry a large part stock, and as we roll out to a distributor model in the future, large part stocks will be carried by the distributors also. This business is all about the customers. The beauty of the situation we have at the moment, where essentially we have control here, we own everything, is we can decide all of that. We're not held to ransom with expensive parts from other customers. We make these parts as inexpensively as we can, so we can carry stock here and in the other territories around the world that we sell in. So expect better from us. But it will take a while to get there. Be practical. You know, we have to get to that stage.
Perfect. How long can you stay in the air with the helicopter before you needing to refuel?
Oh,
I know we have the practical, you know, if you're flying 140 knots, it's a 5-hour fuel tank, 700 nautical mile range. But I know you talked about the other day, if you're not using that, you know, full max continuous power, you can actually stay in the air quite a bit longer.
A long time is the answer. It depends. Are you talking about a sort of modest cruise speed, or are you talking about minimum power speed and endurance? I think endurance is about 8 hours if you fill the fuel tank up. So at that point, You'd only be able to carry 3 people, but you could have about 8 hours. We'll probably be able to improve on that in practice, but simple sums gives you about 8-hour endurance.
There you go. All right.
You would really need the toilet by then.
There are other needs than fuel after that. Yeah. All right, so Ronald asks, with the use of cooling air, how would you manage thermal expansion and condensation?
So thermal expansion and contraction is very difficult on those components. And we have to manage it very, very carefully. It's not a simple answer, I'm afraid. The downside of the annular combustor is that not only do we get extremely hot air on the blades and then cool compressor delivery air essentially packing the upper and the lower portions, but we also get significant variation between the blades. So it comes down to a careful balance between trying to meter the air that comes from the secondary air systems, the cooling air that we use to cool these components, balancing that between the through flow, the stuff that goes over the top and the bottom of the blade rows, and then also tuning the stiffnesses of these components very, very carefully to keep them just at the point where they can just about survive the environment. It's actually an incredibly difficult design task, and we've got some very wise, very experienced people supporting on that. So it's not simple, I'm afraid. There's no simple answer.
Okay. Thomas asks, are you planning on conducting your own type ratings on completion or using a pre-existing ATO?
So we'll have to do it at first, purely because there won't be enough machines out there. So PP4 and PP5 are intended for demo flights, type ratings, early training of pilots, instructors and examiners. But our intention is to push that out everywhere as fast as we can. So a lot of the early training, other than early owners, will be to instructors and examiners around the world. So there's boots on the ground in all of the countries that these helicopters are going to land very shortly.
Okay, Adam asks, what do you expect? Are you still expecting to obtain the 5,000 hours time components without any calendared components in between?
Yes, absolutely.
All right, that was clear.
Okay. We already answered this one in the chat, but may as well just answer it again publicly. So Mornay was asking, do you accept cryptocurrencies for payment?
Yes, we do. We've got an exchange called Coin Corner that you can use that accepts Bitcoin. We as a company don't accept it, but they exchange it into sterling. So you still carry the currency volatility, but you can pay for your helicopter via that exchange in cryptocurrency.
Okay. What are the feature and controls proposed for the cyclic and collective switches, buttons, etc.? Features. Get a little bit more juice on that information. I think that's the question from Sean Gordon.
From Sean Gordon. And just a little shout out, Sean Gordon is currently training at BC Helicopters right now. So
whoop whoop, Sean. Okay, so the cyclic and collective are very, very conventional. So on the cyclic, you've got your push to torque trigger, you've got an autopilot trim switch, you've got an autopilot off, you've got a plus and minus toggle switch that allows you to scroll through memory channels for the radio, and your conventional flip switch to turn standby into active. And then as he glances at the picture over there, that's everything on the cyclic. There is one thing that we might tweak in the future, but I'm not going to talk about that in much detail here, which is how we do the autopilot. We might move the autopilot feature to triggers on both the cyclic and the collective, but that's something that we've got to develop out a little bit further before we talk about it. On the collective, unlike a lot of the helicopters you'll be familiar with, there isn't a twist grip. Because it's an electronically controlled engine, you've just got a fly and idle button like you have on the Bell 505. And then you've got your hydraulics off button and your landing lights button, both toggle switches on the collective lever. So very simple, very intuitive, very similar to what you will have been used to. Okay.
Steve has a question on the mast. So basically on the edge of the weight of the aircraft, bearings, I think he's talking about the bearings that are up there. How is the heat and viscous friction addressed, managing fatigue?
So the heat, the main rotor gearbox has got a forced lubrication system which deals with a lot of the cooling as well. So the main rotor gearbox and the engine gearboxes have oil coolers. So there's a forced lubrication system on the gearbox, and that essentially manages the vast majority of the heat extraction from the mechanical components. So again, very conventional to what you will have seen on other types. The reason that you go to titanium with the mast is purely for its fatigue properties. You can't live with aluminium in an application like that. Yeah, the upside of the upside of these three-bladed rotor systems is you get huge control authority and essentially a nice stiff connection between your rotor disc and your fuselage. The downside is that, of course, puts big bending moments into the mast that we have to react through the structure and through the bearings. So they all have to be a lot beefier than they would have been on a teetering rotor helicopter.
Okay, Brian Thompson asks, happy to see that most of all things are moving nicely along. So what are the challenges that you're facing right now, Jason? Must be some challenges.
Yeah, there's some challenges to do with the digital cockpit. So there's so much detail in putting a user interface together. So working with the various organizations to get that mapped off so that we can release that and get all of the different levels of the digital cockpit working is a large amount of work. I think we've got some challenges ahead of us of getting all of the apps that people want onto that center screen in the DigiCockpit, because the iOS only apps are quite challenging, and there's some commercial hurdles to overcome with that. So that's one of the areas that are pushing, making us think a little bit at the moment. I think there's some challenges with physically getting kit here. So all engineering, like the whole engineering industry has been shut down for a while with COVID. So supply chains, it's not the materials that are the challenge for us, it's getting the kit that we need to start producing these bits fast enough that's quite demanding. So I'm constantly pressing, shall we say, the supply chain to get these things here fast enough to allow us to stay on track with everything that we need to do. So I think the way I would summarize it is the technical things as yet are working very nicely. We really haven't had any really challenging technical problems. That's been quite nice. It's more the crossover between technical and commerce that's been challenging, certainly in terms of the avionics. And then just physically getting kit here, the everyday problems that everybody experiences with a business that's growing very rapidly, getting people fast enough, getting equipment fast enough, you're constantly outgrowing premises. You know, we took the DC on. The DC is not big enough for the casting equipment, so we need DC2 for casting. And it's just stuff like that will keep rolling while we're waiting for the full production facility to be available. So just normal practical things, I would say, are the things that cause me the biggest headaches, not the big technical stuff.
Yeah. And I think the next question kind of follows on to that, so we might just kind of gloss over it, but I'll just read it anyway. So Johan is asking, any risk of delays due to material shortage worldwide? So I think you just kind of addressed that there.
Yeah, I don't think so.
Yeah, okay. Charles is asking, how do you test the lightning strike protection?
with a big lightning bolt. So it has to go to a big electrical discharge facility, and they literally zap it. So yeah, it's not perfectly representative because you can either do high current or high voltage, but you can't do the two together. So it's not quite the same as but there are some standards for testing these things that are mapped out for bigger aircraft, and we just go to a test center and let them do that.
Okay. Stuart Adams asks, I had experience of exterior paint gel coats on carbon fiber boats cracking in extreme cold and also flexing through use. Will you be testing the exterior paint coatings for resistance of stress crackings from extreme temperature ranges? It is minus 31 degrees tonight in Quebec.
Yes. It's the simple answer, yes, to the greatest extent possible. So one of the things that we'll be doing with the third scale model, once we've got the high grade finish one, is exactly that. We'll start looking at paint finishes, and we'll start doing some environmental testing and some accelerated life testing on them for that and other purposes.
Okay. Steve is asking a question on the landing lights and lights on the aircraft. Can you allow for, switching from a regular white light over to a red light if you're going to be doing night flying, so you're landing in twilight or in dark conditions where you may not want to lose your night vision?
I hadn't thought about it, to be quite honest, but I suppose we could. Let me have a think about that, and I'll answer him offline. I think the LED technology will support that, but we just have to have a look at it.
Okay. Chris Fettner. Hi, Chris. Can you speak to the EP with regards to an auto and the deployment of the landing gear?
So auto rotation in the landing gear.
Yes, I think so, and auto deployment.
Okay, so you don't really want auto deployment, because if you're trying to stretch the glide, you want the cleanest airframe possible. So having to deploy the undercarriage will be a pilot responsibility. You'll be warned by the system if you haven't done it when it thinks you should have done, but it certainly won't deploy at the moment the engine fails, because you wouldn't necessarily want that. You'd want to keep the airframe as clean as possible for as long as possible. So part of the auto rotation and the emergency landing procedure will be to deploy the undercarriage where it's appropriate to do so.
Okay. Henny is asking, where will the fuel tanks be situated?
Right behind the cabin bulkhead.
Okay.
So so you've got the monolage, then there's an aft bulkhead that mounts the rear seats, and then there's a second bulkhead that creates the baggage bay, and the fuel tank is in between there. And then there's a small trimmer tank that's located in the nose that we use to trim the fuel CG.
Okay. All right, Jace Holt, with the monolithic design of the fuselage, will minor nicks or dents, especially at critical points such as pillar, compromise the entire structure and require a full replacement?
No, not minor dents and nicks. It'd have to cross a threshold, but you'll have to let us develop exactly what the threshold is, because we've got to do a load of fatigue testing to prove that out. One of the benefits of carbon fiber structures is the fact that they've got lots of discrete load paths within the structure. So they're inherently far more resilient to fatigue than conventional metallic materials. So we can work with that.
Okay. Greg is asking about, will maintenance logbooks be digital or paper? How about tracking downtime and engine preservation requirements?
Yeah, it'll all be digital.
Okay.
Charles asking, will the 4-axis autopilot rely on radar altimeter? If so, any concerns on the recent 5G interference on airlines?
There's no plan for it to rely on a radar altimeter.
Okay.
So I am obviously concerned about the 5G interference.
Yes. There's no plan. There's no plan. I am concerned.
Yeah.
Okay.
Yeah.
Louise is asking, when is the first flight planned?
End of the year. If everything goes to plan, we'll have the prototype together by the end of the year, and we'll fly very shortly after that.
Okay. Gerald, each time you buy one, do you have to do the school? That's a good question.
For a HX you do, yes.
Absolutely. Yeah. Good question.
Okay. Thomas is asking, it's a similar question. Will you be developing a simulator for flight training?
Lots of people have asked about this, and lots of our existing customers have got contacts and want us to do this. Yes, we will, but it'll be once we've got the headspace to do it. At the moment, we're just maxed out with getting the aircraft and the engine developed and approved. So as soon as we've done that, I think there are lots of things that you could do in a simulator that you can't do in a real aircraft that would be really beneficial. So yes, that will form part of what we do once we've got the aircraft into production.
Okay. Jim is asking, still regarding the build school, how long do I have to stay at the factory to complete and check out?
And
2
also,
weeks.
yeah, and also the checkout. So he's asking as well about the flight training.
We can be more flexible about the flight training. You could potentially do that at a different time if you wanted to. You could potentially do that ahead of your build slot in a different aircraft, or you can append it to the end of the 2-week course.
Okay. We already had that question. So Jerry is asking, how many knots will we be lost in the cruise speed if you choose the float option?
None. 0 knots.
Good answer. It was a trick question.
Yeah.
Okay.
All right, a very quick one from Jeremy. How do I get those cool jackets? Well, it's going to be ready in a couple of months. That's the place where disruption exists. Textile has a lot of disruption on the supply. It's easier to manufacture a helicopter right now than having merchandise. Incredible.
Yes.
There you go.
Dave is asking. Yes. What is expected for the warranty? So FBO maintenance process for us in the UK and near Europe, is it an easy logistics problem to get back to the Hill factory? What about the rest of, or it is, what about the rest of the world?
So I think the maintenance will be delivered by your local service providers. So we will operate in much the same way as a lot of car dealers do, in that there'll be book times for certain things, certain approved procedures. There'll be a ready supply of parts, and I think in the early years in particular, it'll be a case of swap the part and send it back to us, and we'll send you a new one to keep things simple. I don't want lots of complex parts being opened in the field, so it'll be a very simple process delivered by people that you trust on the ground in your country.
Very good. Jason, we have very good questions, huh? Very good, very technical today. All right. And this one is different from Chris. Hi, Chris Fettner. And he has a different question. How do you feel about capitalization of Hill right now? Are you comfortable with the current CapEx, burn rate? And have you been able to secure additional UK grants where a part of the initial projections?
I feel great about the finances, largely because sales have far exceeded my expectations. So we're in a very, very strong position. In terms of the factory, that's something that we're working on right now and looks amazing. We've got a very simple route to get the factory financed. And then in terms of the equipment, we've got great support from asset financing partners that support the production of these sorts of machines back there. So yeah, we look good. The burn rate's under control. Sales remain strong. In terms of grants, we were going for one particular grant, but it's not really an issue anymore, just because of the sheer amount of orders that we've taken. We are still pursuing grants, but it's more because we can, rather than we necessarily need them. So yeah, we're in a great position. I don't really anticipate any problems with finance for the remaining part of the program.
Mm-hmm. And as you say, the sales keep on growing. So if it's good, it's going to be even better.
Yes. Phil is asking a question about maximum seat limit as far as weight goes. What's the maximum weight in the seat?
So I think that the normal standard is that we've been working to is 300 pounds, so 136 kilos. And I'm conscious that we do have some particular cases where we've got customers that might be a little bit over that. So we've got to go and just capture that and make sure that there's enough margin beyond that. But the standard is 300 pounds per seat.
Okay. Steve has another question. I think we have addressed part of this because of the 5G issues. Radar altimeter, I think you have addressed that you are going to be keeping that eye close to that and avoiding what is unnecessary. And then he also asks about, can we get a sticker we can add below the Hill logo behind the door that includes the branding for sustainable fuel capable?
Of course you can.
All right, we can get that one. Because it will take. Yes.
Yes. We've already had a question. This is from Nico about the Hill merchandise, scale models and jackets. So just to kind of address that again, as Ruben mentioned, the merchandise is coming. So all the apparel, jackets, hats, all that sort of stuff is on the way. And we're still looking at probably at least a couple months on that because they're very, very backlogged with it. Scale model is something that we actually are just receiving the first ones, the kind of the tabletop models. And so we're just looking at the quality of those, and those should be actually, I believe they are available right now for ordering. So that's great. But we'll just move on to Roy's as well. Flying the R66 above 110 knots in windy conditions can be a bit bumpy. What characteristics do you expect? Yes. Flying the HX50 at 140 knots in windy conditions. It's a great question.
So I think you did a little video on something very similar recently, didn't you, Mischa, flying an A-Star? And I think the thing that makes the biggest difference is that articulated rotor system, that three-bladed rotor system. So having the flapping hinge that little bit away from the center of rotation, and it means the whole fuselage essentially behaves as if there's a big torsional spring connecting it to the attitude of the rotor disc. So all of the bumps and the knocks that you get from gusts and turbulence, rather than only being reacted by the weight of the fuselage dangling beneath the rotor, you've now got this big stiff spring trying to hold the fuselage locked in that attitude. So fundamentally the thing will ride a lot better. And again, I remember the first time I flew an Enstrom, talking about Enstroms earlier, and that feels really planted. You know, when you're flying that along and you're being bumped around by the wind, it's got a great big high inertia rotor that acts like a big gyro, and then you've got this stiff characteristic that holds the fuselage in the commanded attitude under the rotor. So it'll ride a lot better. You won't get that loose feeling that you always get in a two-bladed helicopter, and you won't feel that you're being knocked around. Of course, you're going to feel turbulence. It's still a light helicopter. And the one cautionary note I would say is, of course, it's got a ducted fan tail rotor, so it has a very big tail fin. So the weather vaning tendency, you've got more than enough tail rotor authority to control it, but it will want a weather vane. So I think you'll find it a lot easier than what you're used to. Bigger, heavier, stiffer, and a higher inertia rotor system.
That's what we like. Great. And by the way, just give you an update. We're going to be having this session until 18 minutes?
18 more minutes.
We're going to close at 2 hours of Q&A, presentation Q&A. So if you want to send your questions, that'll be great. We'll be staying here until the hour. So Gerald has a question that is simple. If I don't have a license yet, should I get it or wait? Wait until I receive mine to learn? Well, that's very simple. If you want to fly a helicopter, including the HX50, you need a license. But you can order before having a license. We have several clients that have ordered an HX50, but they will be either having a pilot to fly them or getting a license, and you have the time for that. That's a good advantage of being waiting for a helicopter a little while. So next one is Jose Luis has a question about the maximum all-up weight in external load, cargo hook configuration for the HC50.
I can't remember the figure off the top of my head. I think it's 1,800 kilos. I haven't looked at that for ages. I think it's 1,800 kilos. You don't have the limitations of the undercarriage, so it's more to do with the lifting and the power performance. So I think it's 1,800 kilos.
Okay. I'll go to the question from Angus in just a moment. Going back to the question on Gerald as well, you know, it's a preference thing, talking about the training. Should you get the training now or should you get it on your own helicopter? If you get your training now at a flight school on whichever helicopter they have, obviously you're going to have more experience when you get your HX50. So it's a preference thing. If you're going to train on your own aircraft, you can definitely do that. But then you're going to be a very fresh pilot at that point. So you have a little bit of time before the helicopter is going to be delivered. You know, my personal suggestion would be get your training now, get a little bit of experience under your belt, and then when your aircraft comes, you know, do your type rating training, maybe a little extra training with an instructor at that point. So that's just a suggestion. So going to Angus's question, what stage are discussions with the CAA? Are they responding positively to the amateur built airworthiness approval route? Can you please detail what test flights will be required post-build and how this will work?
The CAA have been incredibly supportive right from the get-go. I couldn't really have asked for any more. I think we've shared before that the whole route that we're taking through the regulations was co-authored by myself and the CAA. It wasn't something that we visited upon them, it was something that we developed together. And so they're obviously supportive of it. We're busy with the various organizational approvals that we have to go through at the moment, so that runs in parallel with the development of the aircraft. And yeah, I couldn't really ask for any more. I mean, they're obviously very busy at the moment, having had all of the powers returned to the UK from EASA. They're busy upscaling and bringing in new people, and that's a big job for them, and as well as sort of reworking all of the domestic regulations. But again, that isn't causing us any problems at the moment. In terms of the test flying, once your individual aircraft is built, then that will not really be a problem for you. That will be something that will be handled at the factory, and it will be subject to negotiation with us once the CAA has seen the full breadth of the production approvals and everything else that we have to do to release an aircraft to service. So it'll be extensively test flown, but it'll be test flown by us before we release it to service.
Okay. Steve asks another question about Hill Digital Cockpit. Any thoughts regarding low intensity, high contrast night mode to protect our night vision? Did you get that, Jason?
No, sorry, just do that
Okay.
again.
Yep. Okay, Steve has a question about the Hill Digital Cockpit.
Yeah.
Okay. Any thoughts regarding a low intensity, high contrast night mode to protect our night vision? I hadn't pondered a theme, but we were just planning to back off the backlighting from the panel itself to deliver that. I'm not opposed to it. I'm quite happy to do it, but at the moment it's not something we've done yet. But of course it is something that can be done right at the last minute, in fairness, because it's just theming.
Okay. Question from Rowan, and let me just make sure that I'm reading this question correctly. So, is the 800 kilogram load an airframe based limit? For example, if it comes in at 1,650 kilos, so under the 1,800 kilo budget, could we possibly see a 150 kilo increase to allowed load?
No, because there's a number of reasons why there's some margins during development, but all of the certification testing and the approvals testing we do will be based on the stated gross weight. So all of the stuff that bases the fatigue life and the durability of the components and all of the stuff that you have to do to prove this thing's safe, that will all be based on the stated gross weight for internal loads. When we come to do the external load, then that's a point load on the cargo hook. It's a different load case. So it's about the qualification of the structure.
All right, short question from Barry. Yeah, you're going to say something, Jason.
No, I'm glad I didn't say it.
Okay.
Okay,
keep
I stopped myself just in time.
Yes, that will come for the next one, the February one. Okay.
Yeah.
Barry asks, why did you decide on 3 blades?
I think just to put a caveat on that, I think 3, not opposed as 2, but multiple extras, I think is where the question is coming from.
Whatever.
Yeah.
What is
4 or 5. Yeah.
It's just common sense, unfortunately. You have to have 3 blades to have a hinge offset and all these lovely flight dynamic characteristics that I've just talked about. The more blades you have, the better the acoustic performance of the helicopter and the smoother it's going to fly. So I would have loved to have had more blades, but what happens is the rotor hub gets bulkier and bulkier and bulkier. And so the donut cowling that we've got at the top to reduce the hub drag starts to get bigger and bigger, and that's a very dominant part of the overall fuselage drag. So to keep the hub as small as possible, you end up with 3 blades. Then on top of that, blade fold is a big deal for people that are coming from 2-bladed helicopters or people that live in inner city areas and put their helicopters in airport hangars. And so folding 3 blades is a lot easier than folding multiple blades. And so it was complexity, cost, practicality, and trying to protect the overall drag position of the aircraft for the maximum possible cruise speed. I wouldn't be surprised if we looked at something with more blades in the future, but I think as an entry-level turbine, 3 blades is the right place to be.
Okay. Next question is from Raul, but before that, just a note or a comment from Martin. He says, I'm very pleased with my purchase after sitting through the first, for me, monthly update. Thanks for doing these, and mega kudos on all the great progress. So the question from Raul is, hello, Jason, Andre from Guatemala. 2 questions. First is whether the tail fin was manufactured in the same composite manner as the monologue. And second, how many people will it require to do the build of the 51% of the HX50, and how long will it take?
From a customer's perspective, they'll only need to be there themselves, and it will be 2 weeks. From our point of view, I can't actually answer that question yet because it depends on how we set up the production facility. But we're working on a rule of thumb of about one full-time person per aircraft per year. So at 250, we'd have 250 employees, and it'll scale with that.
Okay. Dave asks, can we sign up for a long-term lease contract with full service from Hill? So including insurance, maintenance, and provide fluids in the pilot to convert our purchase of a CapEx to a known OpEx based on usage.
Yes, but not yet. So yes, that's definitely something we will do in the future. It's really important, but we're not in a position to do that yet. It'll be once we've got the thing to market. It'll be how we open the market up further.
That's called a yes will come.
It will come. It will come.
Yes. We're down to the last 8 minutes.
Let me just add one other thing to that, of course. The subscription-based maintenance and the underwritten insurance will be available from the get-go. So you're 90% of the way there anyway. And it's only when you drop off the end of your warranty that starts to become an issue, and it will be in place a long time before that.
That's right. Next question is from Steve. So we're just in our last 8 minutes here, and we're just going to have a few questions left. But when delivered, will we be able to get an export of all the parts, serial numbers, and parts revisions in the Hill app? And that would help with tracking maintenance?
So the aircraft will be fully digitally documented. So we obviously have to create huge amounts of documentation as part of the production process. And there's no reason why that couldn't be shared with individual owners. So you'll have a full build log of the aircraft, which tracks everything that goes into the aircraft, including all the NDT and everything that went into qualifying that everything was the way that it should be. So yes, you can have all of that kind of data as part of the build log.
All right. Yeah. For Mark, living in Canada, how long will maintenance? How would I do the maintenance of my HX50?
So basically the same as you would with any other aircraft. So as part of the purchase, you get to send a local mechanic that you trust or have maybe used before to be rated on the aircraft by our training centre here in the UK, and then he'll be able to deliver the maintenance locally for you as he would with any other aircraft.
Okay. Another question from Steve. So is there any plan to use blockchain for traceability of parts? So the blockchain basically that crypto is based off of.
Yeah, there are a number of learned members of the customer base that have suggested that we do this. It's not something I personally know very much about, but we will look at it, and if it makes sense, there's no reason why we wouldn't seriously consider it.
Okay. Raul from Guatemala asks about, that's a very question I think that everybody wants to ask. Will the time of 2.5 years delivery after reservation will be reduced in the future as time progresses?
So there's a number of things that go into make that timeline, isn't there? There's all the engineering that we've got left to do. There's the engagement with the authorities around the world. And then there's demand, because we have to pitch where we set demand, where we pitch our production rate for future years based on what we see the demand going forwards. So the more aircraft that we pre-sell, the larger will be the production rate ramp that we can do, and so the sooner will be the early serial numbers delivered. So if orders continue to come in at the rate that they are at the moment, we will have little choice but to ramp harder and faster. And that will potentially mean that earlier serial numbers will get delivered sooner than they would have otherwise been. So it works for everybody. The more support we get, the faster these helicopters will trickle off the factory floor. Okay.
And 2 questions similar from 2 different Johns. So is there an update on the blade folding and electric folding for the blades?
Not at the moment. That's not a focus at the moment.
Okay. Ryan Shields asks, will the rotor system be high inertia?
Yes. Similar to a Jet Ranger.
Okay. Just getting down to the last couple of questions here. So Elliot, your terms and conditions state that you have required for the pilots to have a minimum of 100 hours pilot in command in rotary aircraft before they can carry passengers. If the HX50 can be used for training, will you be removing this requirement?
I don't think that applies because you're not the pilot in command, are you, when you're using it for training?
Okay.
Okay.
But what I would say
yeah.
is our requirements for instructors will be equally strict because other manufacturers have had problems like that before, and we need to learn the hard-won lessons that they've learned. So we have to be careful about who trains people to fly, and we have to be careful about safety.
Okay. Ruiz asks, will there be a maintenance facilities in every country?
Yes, wherever we sell aircraft into, the owners of those aircraft get to appoint technicians that can come and be trained. So it's incumbent on the owners to appoint or find somebody that they trust, or a maintenance organisation that's convenient for them, and then we will happily train them and support them remotely from the factory to make sure they can deliver the care on the ground.
Okay. Henrik is asking, in December 16, 2021, the webcast that we did, you stated that summer 2023 will be the delivery of the first HX50. Are we still on track for that?
We are as we speak today, yes.
Okay. Dennis, what are the anticipated and sales figures by the Model X and C by the time the first C is scheduled to be released? So by that time, 2026, how do you see the split of the both markets?
I still think that X will be the stronger seller by a long way. I mean, if you look at the aircraft that are registered on civil registers around the world, in one form or another, about 80% of those aircraft are privately owned. And I imagine that the private owners will continue to prefer the HX model because it just offers so much better value and so much better operational flexibility. So I think X will continue to be the biggest seller. And then I think on over a longer time period, I think the fact that C offers such a compelling commercial proposition will trigger growth in the light helicopter industry in a way that other machines won't be able to do.
Okay. Donald is asking the question, when the HC50 is certified, will an HX50 be in a position to move from its permit to fly?
No.
Okay. And X is always an X.
Yes.
Dimitri asks, progress with the UX, user interface.
As I said in the earlier question, so we're right down in the weeds with it at the moment. So we're designing all of the detail of the lower level menus and how that interacts with the Avidyne box, and all of the things that need to be defined before we can push that final development out to Rightware to get the CANSI implemented. So it's moving along nicely. We've got plenty of time to get it done, but there's lots of detail going into it at the moment.
Okay. Melvin asks, out of my ignorance, how feasible is today to use ceramic components in the high temperature parts?
It's not practical. The ceramics have amazing thermal properties. They have amazingly high melting temperatures, but they're just too brittle. So they have a very low fracture toughness, and they're just not robust enough to use in an environment like a gas turbine engine. Lots of people have tried to do it, and there's fancy ceramic composite materials and things that are constantly being offered. But I think for as long as we use gas turbine engines, we'll be stuck with the nickel-based superalloys. And so in terms of the questions earlier about efficiency, it kind of is what it is. In the bigger engines where you can get the cooling passages in and do effective cooling, you can get much, much higher temperatures and make the engine more efficient. For the little engines where you can't get cooling passages in easily, you'll be a little bit more limited. So no, I don't think ceramics have got a place in turbine engines of this scale and of this price point.
Jim is asking, if you want to fly a checkout on an external helicopter, will it then cost extra? The last time I got a checkout on the Airbus was the time 2 weeks, a week technically, and a week training with the completion checkout. That is, the 2 weeks of technically are added to 1 week of training. That is, I have to expect 3 weeks with you then.
Yeah, I understand. Does he need more time at the factory is what he's asking?
I think that's the question, yes.
I think as a worst case, assume that's yes, but we're working very hard at the moment to try and streamline the whole build school process and make sure that we can get everything that we need to done. So just leave that with me. That will continue to develop as as we get closer to delivering that.
Okay. We're already just a little bit over our time, and I think we're just going to take the last couple questions here, and then we're going to wrap it up. Sean Gordon is, I think, a follow-up question to an earlier one. It's saying you also need 100 hours of PIC time, question mark. So I think that's referring to the purchase agreement that somebody asked about earlier. I believe that's nullified if you have the build school. Is that correct, Jason?
Yes, I think it is.
Yes,
okay.
Exactly.
Jonathan asks, have you been getting any job applications from Enstrom or any other struggling companies for employment?
Yes, everybody wants a job. Yeah, we've got applications coming from all over the place at the moment, so it's quite a nice position to be in.
Okay.
So what about one each, Mischa? We wrap it up.
Yes.
Gary is asking, how tall is the highest point of the HX50? We can send to you, Gary. I'll take note the file, but for everybody to hear, we don't have from our top of our head, do we? Any of us?
I think it's 3.2 meters at the tip of the tail, but you'd have to pull the drawing out.
Yeah, but Gary will send it to you. I took note. Okay, Mischa, you can do the last one.
Yeah, Louise. So this will be the last question. The team, great one, seems to be mechanically orientated. What about the embedded software systems team? Any numbers?
That's a much more modest team at the moment because, again, a lot of the clever software is from third parties. So your certified software all comes from Avadyne. And in terms of the FADEC system and things like that, that's a very, very small team. At the moment, it's just headed up by Martin with some external subcontractors, but we are recruiting into that team at the moment.
Great. Okay. Fantastic. We have reached the end. It has been 2 hours and 3 minutes. Mischa, has been incredible. Incredible experience here with our first live stream with our own platform. We had 1,134 people watching live. Amazing. We broke all records. I think the last time was 160 or so. So it did work. We did outgrow the platform, 1,134. Amazing to have you all. Obviously, we lost a little bit of that face-to-face, but as Jason said, we're growing so fast that we have to accommodate that growth. We appreciate your support and trust from everybody. And if you haven't joined yet this amazing community, you're still on time. Right there, Jace, you want to say a few words and then we close it?
Yeah, absolutely. Well, first of all, thank you very much for attending. Thank you very much for all of the searching questions. We're always happy to be transparent and to answer anything you've got. I can only say again what I said earlier, that the support we've received, the resonance that we're having with the market is amazing, and it empowers the program. You know, the more people buy aircraft, the faster that we can work, the faster we can scale up, and the sooner you can all get your helicopters. So it's a lovely symbiotic relationship. It works for all of us, and that's really the culture and ethos of the company that we're building. You know, this aircraft should make general aviation and should make flying helicopters better for everybody that wants to do it, and that's what this is all about. So thank you for your support and thank you for your time.
Wonderful.
Good evening, good day.
Have a good evening, good day for everybody.
Bye-bye.
Thank you.